Good day and welcome back to our discussion on double integrals. This is part 2 of the discussion on iterated integrals, which we introduced in the previous video along with several properties. In this video and the next, we will continue on by just investigating a few examples. Now, let's begin by recalling those properties. If we are evaluating a double integral over a rectangle, so let's say AB times CD, remember notationally that first interval is telling us where the x value will lie. The second interval is telling us where we will find the y value. The first property was something that we called Fubini's theorem, and I'll just write Ft. And it is essentially telling us that for a rectangle, the order of integration does not matter. I could first integrate with respect to y, and then second with respect to x, or vice versa. But just recall, however we go about this, we work our way from the inside out. We first take care of the inside integral, then we take care of the outside. The property we finished the video with was by noting if that integrand function separates into a function of just x times a function of just y, and if you are integrating over a rectangle. So you need both of those things to be true. Then we can break up this new concept, a double integral, into two hopefully simpler single integrals. We could have the integral from a to b of g of x dx multiplied by the integral from c to d of h of y dy. So let's go ahead and take a look at our example. For the rectangle given by 0, 1 times 0, 2, and reminder once again, this first interval is for x values, second interval for y, we are asked to evaluate this double integral. But let's go ahead and make a few observations. The first observation I want to make is this previously discussed property does not apply. That is to say, no matter how hard we try in this case, this function does not separate. That is, I am unable to write it as a function of only x multiplied by a function of only y. But that's not a problem. That means we just have to evaluate it, similar to previously, but that does give us a choice. We need to determine which variable to integrate with respect to first, and my hint is that one choice is maybe easier than another. So as I rewrite this down, think about what variable you would prefer to integrate with respect to first. And I've given us kind of a blueprint or template to work with. Somehow we would like to determine which variable to integrate with respect to first. And this is my intuition. I want to evaluate the simplest possible integral first. And the observation that I'm going to make is that if you look at the x squared y and think of that as being maybe a u, up to a constant, we almost, I'm going to put a question mark there, it's not quite, but we almost have du left over. And that would be du left over when you differentiate with respect to what variable, x or y. So WRT with respect to x. So what I'm going to go ahead is use that observation that I want to do a u substitution with respect to x, and I'm going to put x on the inside and y on the outside. And I will just note that the integral with respect to x we can evaluate with a substitution, whereas the integral with respect to y, you would have to use integration by parts. So I think the substitution is preferable, though the integration by parts will certainly come up in a future example. So doing our work to the side, we're going to let u be x squared y. Du would be 2xy dx. And looking at our integrand, we have a u. This xy and the dx is going to combine together to be 1/2 du. So no, 1/2 du is xy dx. So in terms of rewriting this, we have this outside integral which still remains. Then on the inside, we have a 1/2, which is a constant we can pull out. Limits of integration that need to be determined, e to the u du. And with a substitution, we always change our limits of integration. We start off with x equals 0, and if we look at our substitution, u would be 0 squared y, which is 0. That gives us our new lower limit of integration. In terms of the upper limit, when x is 1, u is 1 squared times y, which is y. And our upper limit of integration becomes the variable y. And that's perfectly reasonable for the inside limits of integration to involve one of the variables, specifically the variable on the outside. But the outside limits of integration always have to be constants. And now we're in an ideal position to integrate. So the stuff on the outside is going to remain there until we take care of the inside. The antiderivative of e to the u is e to the u, and we're evaluating from u equals 0 to u equals y. The fundamental theorem of calculus tells us replace that u with a y, minus sign, replace it with a 0. E to the 0 is the number 1. And if we would like to, we can go ahead and pull that 1/2 out front. The antiderivative of e to the y is e to the y. The antiderivative of 1 is y. And this is from 0 to 2. So we replace each y with a 2. So e squared minus 2. Minus sign, we replace each y with a 0. And note, e to the 0 once again is 1. So what we end up with is the 1/2 hanging around out front, e squared minus 2 minus 1, which completes the example. And just to kind of finish with an observation, remember if it did happen to separate, that would allow us to break it up into 2 single integrals, which is kind of a nice scenario, but as we see very clearly here, will not always happen. And additionally, when we set up our order of integration, we would like to kind of make the inside integral as simple as possible for us to evaluate. In this case, the inside integral being x allows for a substitution, whereas alternatively, the inside integral being a y would result in an integration by parts. And for additional practice, you could certainly evaluate it using that opposite order of integration and double check that you get the same answer. So in the next video, we will look at an example that does require integration by parts. So stay tuned and take care.